You're missing a great lesson. Okay, we're going to go over some of the homework.
Yeah, why is Alex though? It's a waste of time.
This was number one. So, looking at particle motion analytically, we're given a... I don't know what you just said, Paul. That was incoherent. That was a concussion talking.
I mean, I got a concussion yesterday.
They've given us a function that describes the position. So let's go through and see if we can answer these questions, knowing what we know about motion. What's a displacement? How do I find displacement from position?
It's change in V over T. No.
Displacement is a change in
X over T.
right, it's a change in position. The delta x, change in position. So I need the position at one end at time b. The position at time a. The difference is my displacement. So I need the position at x. I'm going to evaluate that function at 6. Okay. Did we try that? Did you type that in? You can do it by hand. You can do it by calculator. Or was it?
That's all you have to do.
Like B through F.
Did I do what?
B through F.
Do what?
Do like B and F.
D and F?
No, you said B through F.
Yeah, we'll go through all of them. We'll go through them all. Because this is a classic, it wraps up all the features of a classic motion problem on the AP test, on a chapter test, and we want to be able to do these rigorously with all the explanations needed if needed, show all the work is needed. Okay, so you just substitute into there, and you get negative 96. I'm not going to do the algebra for that. You can evaluate that. And if you evaluate x of 0, no, I'm sorry, that was negative 100.
I got 8.
8.
I got 8. I got 8.
What did I do?
I got 8. I got 8.
Putting in 6?
Let me
8 and then negative.
Negative 1.
Yeah, it's 8 and then negative.
So you get 12.
Yeah, 12 and then 6.
Oh, I did cube. You're right. You're right. I put in the wrong number there. What did we get? What did we get here? 8?
8.
And this was negative 4. You're right. I put in the wrong number. And delta x is therefore going to be 8 minus negative 4, which is just 12. Find the average velocity. Average velocity is going to be my change in position divided by my change in time, or displacement divided by change in time. Well, I just found the displacement. The displacement was 12. And the change in time in the first 6 seconds, 6 seconds. My velocity is, my average velocity over the first 6 seconds is 2.
What?
Units of time per units of second, whatever the units were. Okay? So there's my average velocity. Now we want to find expressions for...
Velocity and acceleration?
Yeah, for v. Velocity, as a function of time, will be the derivative with respect to time of the position.
Acceleration is derivative.
Will be the
Velocity.
right, or the second derivative. So let's take the first derivative. What's a derivative of 1/3 t cubed?
T squared minus 6t.
T squared minus 6t plus 8. There's my velocity. That function gives me the instantaneous velocity at any time. That's my instantaneous velocity at any time. And sometimes you'll find that the instantaneous velocity is different from an average velocity. It often is. Okay, acceleration. Well, I'll just take the derivative again. Take the derivative with respect to time of v of t. That should be an easy derivative to take, right? 2t minus 6. And again, that's the instantaneous acceleration at any given time t. What's the acceleration at time 1? 2 minus 6, and so on. Okay, that was C. How about D?
So the calculator for the for Ruby, let's do the breakdown.
Or what's D here? D wasn't there. Okay.
We used to flip the next page.
Yeah, did I have the next page? I'm not sure. Let's check. Yes, I do. So let's kill all of that.
Wait, why'd you do it? You already did it the other class?
What other class? That was from last year. I actually saved it last year.
Oh my gosh. So you haven't taught this since last year?
No. Okay. When is the particle at rest? So when is something at rest? When the velocity is what? 0. So we're going to find where the velocity was 0. But we just said the velocity was what? T squared minus 6t plus 8. So I'm going to set the velocity equal to 0, which means I need t squared minus 6. Was it minus 6t? I got it right here. T squared minus 6t plus 8 has to be 0. Well, when is that 0? Well, I can find the zeros of that. How am I going to find the zeros of that? Factor it. Yeah. We shouldn't need a calculator to factor that. That's a binomial easily factorable. Okay, what are my two factors? -4, -2. So when is a particle at rest? At t equal 2 and t equal to 4. Those are my two zeros in the velocity function. At those two times, the velocity is equal to 0. Yeah, we're going to get into optimization, all that. You will find local maxima and minima at the zero of position at the zeros in velocity. They'll correspond to the horizontal tangents where the derivative is 0. That's going to be another discussion for another chapter. But you probably did some of that with Miss Brown and pre-calc. Okay. Now, this part, on what intervals is a particle moving left and right? This part here is where we're going to make a little number line. Did you guys do sign charts last year? Yeah? Maybe? Carly, did you do sign charts last year? Yeah, okay. We want to find the intervals on which the particle is moving right and left. Well, when it's moving right, the velocity is positive. When it's moving left, the velocity is negative. So what I need to figure out is, well, where is the particle, where's the velocity positive, where's the velocity negative? Right, so I'm going to start out at 0. There's a 2. There's a 4. If your time is starting at 0, unless they specify some other time interval, we're going to start at 0. Really? This is my hand is not that shaky.
Looks pretty shaky. You got it. Almost. Swing and a miss. 0, 2, 4, and it goes on. Okay. So I know, so here's the big concept. I know that the velocity is 0 at time 2, the velocity is 0 at time 4. There's the only zeros. So it can't be 0 anywhere else. And from intermediate value theorem, we can check the 0 also, but from intermediate value theorem, for example, between 2 and 4, if the only zeros occur at 2 and 4, in between it's always going to be positive or always going to be negative. It can't switch from positive to negative in between because there's no other zeros. So I'm going to check values on each interval and see if it's positive or negative. Negative, that would be huge.
Yeah, so let's check a value at 1. What is the velocity at 1? V of 1 is, and if you have it factored, the factored form makes it so much easier. Because when t is 1, this is negative, and that's negative. The two negatives make a positive. So I know between 0 and 1, it has to be always between 0 and 2, it always has to be positive. Let's check v at 2. No, v at 3. That's in the middle of the next interval. When the time is 3, my first factor is negative. My second factor is positive. Negative times a positive is a negative. So, and then we can check greater than 4. Let's check the other end. Let's check v of 10, say. When the velocity is 10, are they both positive? Yeah. So I've got a positive here. Wait, not even close. Ha! Stupid smartboard. So what I did was I set up my number line, laid down my two zeros that I know. They're the only two zeros that I can check a value in the middle of, or somewhere within each interval. It doesn't have to be exactly in the middle. And you can check the sign. Positive here, negative here, positive there. And since there are no other zeros, I know for certain that it's got to be negative everywhere in the interval from 2 to 4. It's got to be positive everywhere in the interval from 0 to 2. It's got to be positive everywhere in the interval from 4 out to infinity. It doesn't cross 0 anymore. You can't have any more sign changes. I can't change sign without a 0 if it's continuous, and that's a continuous function. So if I want to finish answering the question, on what intervals is a particle moving right? It is moving right on the interval from 0 to 2 and 4 to infinity. Zero to 2, 4 to infinity. When is it moving left? It's moving left between 2 and 4. You can write it using interval notation, you can write it using inequality, it doesn't matter. Not including the 2 and the 4 though, because it's not moving in any direction at 2 or 4. Well actually, I should include the 0 here though. The 0 is not a 0. Realize that. 0 is just the start of my interval. When time is 0, it does have a positive velocity. We're starting counting time when it's in motion to the right already. Okay, there's a sign chart. Now, if they ask you to justify your answer, the sign chart by itself is not sufficient justification. You want to show your calculation, show your sign chart. You want to put it in words. Why is it moving to the right on these two intervals? Because that's where the velocity is greater than 0. Why is it moving to the left on that interval? Because that's where the velocity is less than 0. I would say that in words if it asks you to explain or justify. You know it's moving to the right when the velocity is 0. Those are the intervals when the velocity is greater than 0. Those are the two intervals where the velocity is greater than 0. When is it moving to the left? When the velocity is less than 0. That's my interval where the velocity is less than 0. How do we feel about that? Okay. We can do the same thing for acceleration. Works exactly the same way. Should we do acceleration? Let's do it.
I think we can do it.
Let's do it. Okay. When is the acceleration 0? Well, my acceleration as a function of time was given by 2t minus 6. Okay, there's only one 0 there. And I can set that equal to 0. And the only solution is t equals 3. So my number line's a little bit simpler. Yeah. 0, 3. It's going to be positive on one side, negative on the other. We've got to figure out which one. So we pick a value within one of the intervals. Let's pick 1. A of 1 is what? Negative 4. And let's pick 10. It's A of 10. 20 minus 6 is 14, positive. So on this interval, it's negative. On that interval, it's positive. So what intervals is a velocity increasing? Well, we know the velocity is increasing when the acceleration is positive. Increasing from 3 to infinity because velocity is, sorry, acceleration, we did velocity already, is acceleration is positive. When is the velocity decreasing? Well, the acceleration is negative. That's from 0 to 3 because the acceleration is less than 0. Okay. Happy about that? Should we do the tricky one now? Let's do a. How about the speed? When is the speed increasing and decreasing? When is speed increasing? When what?
Velocity and acceleration are the same sign.
Right. You're going to look for when the velocity and the acceleration are the same sign. What I'm going to do is take the two sign charts and combine them. Oh!
That's not tricky. This is a lot of work.
It's not a lot of work. I what?
We did this in
Good.
We just never told us what we're doing. We just found the numbers.
Oh. Okay, now we know what we're doing. We're going to focus more on the concept here. So, the concept says that speed is increasing when velocity and acceleration are acting in the same direction. Goes back to our spaceship game. Combine my sign charts. 0, 1, 2. Oh, do I have? Oh, I didn't have a 1. There's no 1. 0, 2, 3, 4. There is no 1. Okay. Well, between 0 and 2, are the signs the same or different? Different. So speed is negative. Between 2 and 3, let's look. From 2 to 3, velocity is negative and acceleration is negative. Both are negative, acting in the same direction, positive. From 3 to 4, from 3 to 4, what's my velocity?
Oh, it's negative.
Negative. From 3 to 4, acceleration is positive. Different signs.
Negative. Different outcome.
And then beyond 4, the velocity is positive, and the acceleration is positive. Same sign. They're both acting in the same direction. So, on what interval is the speed increasing? Where the signs are the same, that's 2 to 3, and 4 to infinity. Because, yeah, I had to make a combined number line. Because acceleration and velocity have the same sign. And when is it when is the speed decreasing? On the interval from 0 to 2. And 3 to 4, because the acceleration and velocity have opposite signs. Okay. How are we feeling about that? Sign chart will help us figure out what to test. We want to summarize it with some sort of words down here. I kind of shorthanded, abbreviated there, but write it out in words. What? No! No. We're gonna do some more practice with analytical.
I like that. I like that.
You got next page, right?
Oh, mine doesn't have.
Yours does.
Trying to trick you.
Let's see. Is that what you're?
Don't be silly, man.
Yep, that's your page set. Okay.
Damn it.
Okay, so do you want to try some of these on your own, or should we start some together?
Together.
Yeah, I like your thinking.
Yeah, like your.
Yeah. Jen, your sister said a bad word today.
What did you say?
Yeah, she did it beautifully.
Who said that?
Why?
Jennifer Powell's younger sister was a freshman.
Oh, I heard Jennifer Powell's sisters are here.
Yeah. She had crackers and she gave them to me.
And I said, what about me? Do I
She
get any
said,
crackers?
she said, F you.
Yeah, but she said the word.
What do you expect Jennifer to do about this?
I don't know.
I won't give her a ride home. I'll make sure.
Yeah, good. Make a walk. I was pretty young.
I think she's gonna tell her sister. Good for you. He probably deserved it.
No, but no, Will did not deserve that. Will deserved the crackers.
Okay.
Who deserves a piece of this?
Are you trying to like promote hate, Dr. Cassandra? I think that's what you're doing.
I think you guys should do this one on your own, because this is just like the previous one.
No,
What do you expect?
I'm gonna pause the video here.